So, welcome friends to this class which is on optimum functions with condition. In the previous class we have discussed about the optimum of a function and the functional and the different cases we have seen. So, with optimum of a function with condition, first we will formulate a problem. Our problem is to find the optimum of a function f which is a function of the two variable x1 and x2, and this is subjected to the condition g x1 x2 equals to 0. So, my problem here is to find out the optimum value of the f which is subjected to the condition g of x1 x2 equal to 0. So, this problem can be solved in the two approaches. The first we call the direct approach and second is the Lagrangian multiplier approach. So, this problem can be solved as direct method and my second method is the Lagrangian multiplier method. So, one by one we will discuss both the methods. Let us first take the direct method. So, what we have to do, if we have to find out the optimal value of a given function f which is a dependent on a single variable. So, simply we will say del f by del x to 0, or as we have discussed previously, the differential of the function must be equal to 0. So, this means if I will write df which is nothing but del f by del x1 dx1 plus del f by del x2 dx2, and normally we say that must be equal to 0. So, my problem is to find out the, we are considering a function f x1 x2 which is subjected to the condition g x1 x2 equal to 0, and my objective to find out the optimum value of this function f x. So, my necessary condition for extrema will be del f by del x1 dx1 del f by del x2 dx2, that must be equal to 0. Now, if these two variables are independent, then we can say del f by del x1 must be equal to 0 and del f by del x2 must be equal to 0. But in this case we consider the x1 and the x2 are not independent. If I treat means the x1 x2 are related to each other, they can have their value. So, independently we cannot say del f by del x1 will be 0 and del f by del x2 will be 0, but as a minimal condition I can say for this my df must be equal to 0. So, this is my necessary condition which we are saying here as a necessary condition for extrema, my df should be 0. Similarly, g is also a function of x1 x2. So, if I will write dg which will be del g by del x1 dx1 plus del g by del x2 dx2, as g is already 0. So, dg will also be 0. So, what we can say, dx1 and dx2 are not arbitrary in this case, but they are related to the relation dg equal to del g by del x1 del g by del x2 dx2, that is equal to 0. So, to find out the optimal value which satisfy both the condition, we arbitrarily choose one of the variable which is x1 as the independent variable. So, naturally in that case x2 will be the dependent variable as per our given condition. So, if x1 is independent, x2 is dependent, what we can do? We can find out the value of the dx2 in terms of the dx1. So, that we are finding from dg equation. So, by this equation, if I am writing dx2, so I can simply write it as minus del g by del x1 divided by del g by del x2 and multiplied with the d x1. So, now if I will place the value of the dx2 in this, so this my whole expression will be with dx1 value. So, in the next we will place this dx2 in df in this expression. So, this means del f by del x1 dx1, due to this will be the del f by del x2 multiplied, negative sign we have considered here, del g by del x1 divided by del g by del x2, that is sorry, and this is also multiplied with dx1 and this equals to 0. So, if I will simplify, so this is nothing but my del f by del x1 into del g by del x2 minus del f by del x2 into del g by del x1 whole multiplied with dx1 equal to 0. So, now in this case my dx1 is arbitrary. So, the coefficient of related to dx1 that will be 0. So, I can say my del f by del x1 del g by del x2 minus del f by del x2 del g by del x1, that must be equal to 0, or we can simply write as the determinant of del f by del x1 del f by del x2 del g by del x1 del g by del x2, that determinant must be equal to 0. So, for extrema of a functional, my condition will be this must be equal to 0 or this must be equal to 0, and this is nothing but we call the Jacobian of f and G. So, what we saying, my condition coming out to be del f by del x1 del g by del x2 minus del f by del x2 del g by del x2 must be equal to 0, or the determinant of del f by del x1 del f by del x2 del g by del x1 del g by del x2, that is going to be 0. So, what actually we have done, if a function is a function of the two dependent variable, one is x1, other is the x2, what we can do, we can eliminate one of the variable, minimize it using the another variable and place the value, because both the variable are related to each other. So, if we can find out the one variable, we can find out the other variable also. That we will see in a very interesting problem. So, my problem here is given as a manufacturer want to maximize the volume of the material stored in a circular tank, subjected to the condition that the material used in the tank is constant. Thus, for a constant thickness of the material, the manufacturer want to maximize the volume of the material used, and hence it has to reduce the cost. So, in a given material, if I will increase the volume, so this means the storing cost I can reduce. So, what my problem is, I am given, you can say, a constant or a fixed material is given, and from this material we want to make a circular tank, so that the maximum volume can be stored into this circular tank. So, let us understand the problem in the following manner. Consider a fixed thickness and let D and H be the diameter and height of the tank, where D is the diameter and H is the height of the tank. So, basically we have to find out what will be the diameter and what will be the height of the tank, so that the maximum volume can be stored, while the surface area of the sheet by which we are forming the tank is constant. So, we can write, so if D is the diameter, H is the height, then the volume of the tank is we can write here, this is a function of diameter and the height, and this is nothing but here pi d square H by 4. The cross sectional surface area of the tank will be, now what the cross sectional surface area, it will have the bottom top and the sides. So, top and the bottom are my circular sheets, while the surface is my cylindrical sheets. So, this cross sectional area, if I will write as a function of d and h, so pi r square is the area of my circular sheet. I have the top and bottom, so I can write 2 times of pi, d is the diameter, d square by 4, this is my top and bottom, plus pi dh is my sides, and this is my surface area. So, what is my problem? I have to find out the maximum volume, so that, so this means I will maximize the volume by selecting the proper value of the d and h, while my given surface area is constant. Let us say this value is a naught. So, this is my extremization problem with a given condition, where my objective is to maximize the volume subjected to the condition given as A. V is function of the 2 variable d and h, because both d and h will be dependent variables. So, if I will treat one variable as a dependent, other as the independent, so I can place the value of the one variable, I can find out the value of the one variable in terms of the other. As my surface area is fixed, from this equation I will write my height in terms of the diameter So, my h is a naught minus, this is pi d square by 2, this is divided by pi d, and I will substitute the value of h. Substitute h in volume expression in VDH. So, this means this h I am placing here, and I will get, so just by placing the value of h in the expression of V, we get VDH as pi d square by 4 a naught minus pi d, or simply I can write this as a naught d by 4 minus pi d cube by 8. So, this is, now I am writing my V only with one variable d. H and d are related by this expression. So, what we have done? We have found out the one variable in terms of the other, place the value of this variable into the volume expression. So, my V is simply as a naught d by 4 minus pi d cube by 8. So, we have eliminated the h from the volume expression. Now, it is a simple maximization problem. So, I have to maximize the V and find out the value of the D which will maximize my V. So, simply I can say my dV by d of d, this d for diameter, that must be equal to 0, and if dV d2V by d of d square is less than 0. So, this will be the maximization problem. So, we will differentiate V with respect to diameter. So, differentiate V with respect to D, what we get? We get A naught by 4 minus 3 by 8 pi d square equal to 0. This implies my d, which is nothing but my optimal value, is square root of 2a naught by 3 pi. So, V to be maximum, D to be 2a naught by 3 pi, H we already have been determined in terms of the D. So, if D is known to me, I can directly write the value of the H. This is 1 by pi d A naught minus pi by 2 d square, and if you will simplify this, again you will get this is 2a naught by 3 pi, which is nothing but your d star. So, this H we can also say my optimal value. So, for this particular case, my H and D both have the value 2a naught by 3 pi. So, in this problem we can conclude we can maximize the volume of the tank if we will make the diameter of the tank same as the height of my tank. So, this is one of the approach to find out the optimum value of the functions with conditions. My another approach is called the Lagrangian multiplier approach, in which we will define a Lagrangian which is nothing but contain both my function and my condition, which are related with a variable lambda, which is called the Lagrangian multiplier. So, this approach we will discuss in the next class. So, in this class I stop it here. Thank you very much.